authors write the material in the book in such a way so that it starts out here on a relatively low level in terms of difficulty, and then it sort of builds up. And remember in the last chapter we built up to those word problems and some other things like that. And then they let that idea go for a while, all right? And then they start with a new idea. So the level of difficulty sort of drops a little bit, and then it starts to build up, all right? And then it reaches some point, and it stays there for a while. Then they pick up maybe a third idea. So as you go through the book, there are these peaks, so to speak, of these various ideas. And then later on sometime, in some other chapter, they begin to take the cream off of each of those peaks, so to speak, and then put those ideas together. And this is how mathematics is developed. Okay? So what we're going to do is to sort of start from the beginning again and look at another idea and a new idea in this chapter 5. Okay? So notice the name of the lesson is called Open Sentences in Two Variables. Now, let's see how we can talk about this idea. Let's go back to a very easy example of something, let's say 2x plus 3 is equal to 11, in which I now want to take, say, well, let me write where x belongs to, in this case, a set of real numbers. And remember, this is our replacement set, okay? And everyone looks at this and says, oh, yes, I can write a simpler name for this sentence, an equivalent sentence in which what? 2x is equal to 8, and of course, x then is equal to 4, all right? And we write our solution set with the element 4, and certainly the number 4 is a real number, and so we conclude that that's our solution set, okay? And there's nothing very new or different about that. Now, notice we have one variable in this equation. And what I'd like to do is to introduce, say, 2x plus y is equal to 11, in which in the one sentence we now have two variables, one called x and the other y, where, again, I have to now indicate some set over which x and y can vary, okay? So let's decide that x, say, belongs to the set of natural numbers, and also let y belong to the set of natural numbers in the example that I have selected here, okay? So now you say to yourself, well, I have lots of choices. All right, and let's see what choices we have. Well, let's start out, in this case, with x. Let's let x, well, if x is a natural number, what's the smallest natural number that we have? And it is, Ron says, 1. All right, so if x is 1, all right, what then is y going to be? If x is 1, 2 times 1 is 2, and y has to be, Steve says, 9, okay? And if, say, x is 2, let's just go up the natural numbers here in order to be able to find all possible values for x, okay? And if x is 2, y has to be, and what? 2 times 2 is 4, so y has to be what? 7. If x is 3, y must be what? 5. Now, notice how I am saying this. If x is equal to, what, 4, then y must be equal to, right? I have no choice now for the value of y once I decide to pick some value for x. So what now must y be when x is 4? And everyone says, what? 3. And now, if x is, what, 5, y must be 1. 1, right? If x is 6, y must be negative 1. And you say, oops, there's a value of y, which is negative 1, which is outside of our set of natural numbers. All right? So this last example that I have included here is not in our solution set. Is that right? Now, notice this is a rather cumbersome way for us to write all of this. All right? In our first example that we had up here, we ended up with x is equal to 4, in which that was a very nice, easy sentence for us to write, and we wrote a solution set in this fashion right here. So, what we'd like to do is to look at all of this as our solution set. This is a rather awkward way in which we have written it here. So let's see if we can invent another way in which we can write it, okay? And let me come up here, and what I'd like to do, now here we have written our set as a solution set with this set bracket notation. So let's see if we can invent some set bracket notation which we can list the elements. Now, notice it says here x is 1 and y is 9. And it turns out that the system that has been invented All right, and that's all that we're going to do now is to make an agreement as to how we're going to write our solution set. And we'd like an easy way in which we can do so. Okay? Now, if we decide to call the first element x in the case that we have here, okay, and then the second element y, let me decide to write this with parentheses in this fashion with a little comma here in between, in which I'm going to write the element 1, 9. Okay? Now, that's one number. This is one element. And we're going to refer to this as an ordered pair. Okay? An ordered. O-R-D-E-R-E-D. An ordered pair. Now, notice the emphasis is on the word ordered here, because 1, 9, there's a specific order in which we have written them, in which the number 1 is first, and in this case the number 9 is second. And now comma here to indicate another element in our set, and what now is going to be another element in the set that we can write. And from our sentences over here, Ron says 2, 7, okay? 2, 7. And now notice I'm putting a comma here to indicate a third element. This is one element. This is an element. This is one element in our set, okay? And the elements consist of ordered pairs of real numbers instead of just real numbers. What then is a third element in our set that we may write? And looking at our data over here, Bob says 3, 5. What's another one? What? 4, 3. And what? 5, 1. And how many elements are there in this set? Counting up the number of elements, Chuck says we have, pardon me? 5. 1, 2, 3, 4, 5 elements in our set, okay? And we refer to the first element here, all right? We can call this the first element or the first coordinate, okay? The first coordinate is another name that we give this, or another word is the first component, C-O-M-P-O-N-E-N-T, all right? And of course, this element here, we would call what? You may call this, well, if this is the first, you'd say, well, this one has to be called the second coordinate or element or component, okay? Or component. Now, notice we have here a list of the elements in our set, in which the list now consists of ordered pairs of numbers. Let me ask you a question. You think is 1, 9 the same as 9, 1? And I think you would agree that the answer to that is no. Let's decide on what we mean by the ordered pair A, B is equal to the ordered pair C, D. When is the ordered pair A, B equal to the ordered pair C, D? When what? What conclusion do you think you can make here? Sally says when A is equal to C and B is equal to D. Is that all right? Everyone agree with that? All right. This is our definition of what we mean by two ordered pairs being equal. When the first components are equal and the second components are equal. Okay? All right. Now, let's then look at, suppose I were to write the element 1, 9 as a set in set notation. The question is the set consisting of the element, the ordered pair 1, 9, equal to the set consisting of the elements 1 and 9? And this is our question that we now want to answer. What do you think we can say about this? On the set on the left, how many elements do we have in that set, David? How many elements are in this set? 1. And that element consists of an ordered pair of numbers 1, 9. Okay? How many elements are in the set on the right? And Sally says 2. Now my question is, again, are these two sets equal? And what's your conclusion about that? And Ken says no. Okay? And the sets are not equal because on the left here we have one element which is an ordered pair, and on the right we have two elements, the numbers 1 and 9. Okay? So you have to be very careful when you start writing our sets in which we're talking about ordered pairs of numbers. You have to include those parentheses, okay? Because the parentheses tell you that this is one element in our set. Okay? Well, let me call this idea number 2, and let's continue on here. And let's look at a third idea. Now, remember back when, well, let's look at our first example. And if we were to write a description of that set, remember the notation that we used was a set of all x's such that, and what was our sentence? 2x plus 3 is equal to 11. Is that right? And where, what? x in that case belonged to the set of real numbers, okay? In which we then gave another name to this set. If we were to make a roster or a list of the elements, I think you will all agree that this list is simply the one element 4. Is that right? Well, let's carry through with the same idea in this example that we have here. Now, instead of talking about the set of all x's, what we now want to do is to talk about the set of all x comma y's, such that something is true. And in the case that we have here, we have what? 2x plus y is equal to 11, okay? And now we have to state what? Where x belongs to what? N, and y belongs to n, okay? And if we were to list the elements in our set, what then would be the elements that we were going to write here? Well, in fact, all I'm going to do is repeat what we have here. 1 comma 9, 2 comma 7, 3 comma 5, right? 4 comma what? 3, and what? 5 comma 1. Okay? Again, notice that these commas separate the elements in the set. Is that right? Whereas the commas inside the parentheses are part of our notation, which talks about an ordered pair of real numbers. Okay? Let's now look at another example. Oh, let me make up some example in which we have here a set consisting of ordered pairs x comma y, such that x plus 2y is equal to 8. Okay? And again, I have to indicate some domain for our values of x and y. All right, so let's decide that x belongs to, oh, let me just make up some little finite set. Let's say, oh, -2, 0, and 2. And let's let y belong to some set of numbers, oh, let's say 2, 3, and 4, okay? Now, this is the set that we are concerned with. I think as you do some of these problems, you're going to realize that what we can do is to look at the sentence that we have here, x plus 2y is equal to 8. Since we normally take values for x first, what we can do is to write this equation in terms of y in terms of x, okay? So here I'm going to subtract x from both sides of our equation, and now let's divide both sides of our equation by 2, and so we have -½ x plus 8, okay? Now, let's indicate if x is equal to what? -2, let's see what values of y we have. So if x is, whoops, is there something wrong here in this sentence? Y equals what? -½ x, and Todd says? Plus 4. That's one of the common mistakes that people make, including me, all right? Plus 4. And now, if x is equal to -2, -½ times -2 is what? Is 1, and 1 plus 4 is, y must be 5. Now 5 is outside of our domain here, outside of our replacement set for x, so this ordered pair of numbers is not in our solution set. Is that right? Let's try the next case. If x is equal to what? 0, what can we say about y? And if we substitute, you see how easy it is to work with this now that we have it written in this pattern of y in terms of x. If x is 0, -½ times 0 is 0, plus 4 is what? Y must be what? 4. Is that right? And so these two elements are in our set, in our solution set, and of course we have what? If x is equal to 2, what is our conclusion about y? We have -½ times 2 is what? Is -1 plus 4 is 3, and 3 is in our set, all right? And so if we were to list our elements, right, we have 0, 4, and 2, 3 as our solution set. Is that right? Okay? Now, let's take another example. In fact, let's keep the same the set here in which we're talking about the description of the set is a set of all x comma y such that, all right, x plus 2y, and let's talk about is less than 8, okay? And again, where x belongs to, let me take the same set, -2, 0, and 2, and let's say y is the set of what? 2, 3, and 4 as I have it here. Okay, now let's go through the same procedures we have just done. X plus 2y is less than 8, okay? Let's subtract x from both sides. We'll have what? 2y is less than opposite of x plus 8. And now let's divide by 2. we have y is less than negative a half x plus 4, okay, plus 4 now. Now, since we're dividing by a positive number, our order of the inequality stays the same. Is that right? Okay? Now, let's go through the same procedure. Let's pick out our first element for x. If x is negative 2, all right, if x is negative 2, negative a half times negative 2 is what? 1. It's positive 1. And 1 plus 4 is 5. Now, y must be less than 5. So it's the set of elements from this replacement set that we can take for y. And we can pick any value for y which is less than 5. So you say, okay, if x is negative 2, give me one value for y. And 4. All right, give me another value for y. 3. Give me another value for y. 2. Oh, now when x is negative 2, we have these 3 different values for y. Okay? Now let's come along and take the next value for x. If x is 0, okay, let's see what happens. Here we have negative a half times 0 is 0 plus 4 is 4. What then is a possible value for y from this replacement set for y? And what then can we say, Ron says? 2 and 3. All right, well, let's put 3 first, and then y is equal to 2. Okay? And then I think we've exhausted all possible cases for y here. And what else can we take? If x is equal to 2, is that right? Let's see what happens. If x is 2, here we have negative a half times 2 is what? 1. Is negative 1 plus 4 is 3, and y can be any number less than 3. So what possible cases do we have for y? Y must be equal to, and Bob says, is equal to 2. Okay? Now, let's write our set as ordered pairs. Okay, let's make a list of our elements in which if we have the first element is negative 2, a possible value for y is 4. So there's one element. Okay? If x is negative 2, a value for y is 3. If x is negative 2, a possible value for y is 2. Okay? So for the first element, in each case of negative 2, we have 3 different elements for y, namely 4, 3, and 2. Okay? In which this is a nice, easy way for us to list those elements as ordered pairs of real numbers. Okay? And finally, here we have what? If x is 0, y can be 3. And if x is what? 0 again, y can be 2. And finally, in this ordered pair, we have what? If x is 2, y must be what? 2. And I think that's all of the elements that we have in our set. How many elements are in this set? 1, 2...